Okay, for our example, we're going to just pull one right out of the book here together. We're going to go to page 264 and we're going to do problem number 12. So problem 12 says the spotlight effect refers to overestimating the extent to which others notice your appearance or behavior, especially when you commit a social faux pas. A faux pas is kind of an error, a mistake. Effectively, you feel as if you are suddenly standing in a spotlight with everybody looking. In one demonstration of this phenomenon, researchers asked college students to put on a Barry Manilow t-shirt, and fellow students had previously judged to be embarrassing. The participants were then led into a room in which other students were already participating in an experiment. After a few minutes, the participant was led back out of the room and was allowed to remove the shirt. Later, each participant was asked to estimate how many people in the room had noticed the shirt. The individuals who were in the room were also asked whether they noticed the shirt. In the study, the participants significantly overestimated the actual number of people who had noticed. So, looking at part A here, it says, in a similar study using a sample of 9 participants, the individuals who wore the shirt produced an average estimate with a mean of 6.4 with a sums of squares of 1.62. The average number who said they actually noticed was 3.1. Is the estimate from the participants significantly different from the actual number? Test the null hypothesis that the true mean is 3.1 using a two-tailed test, 0.05. So, to get our 4 steps in here, step 1. Oops. The alternate hypothesis is the treated population will no longer equal whatever the general population was. And the problem told us that for the general population, it's 3.10. So the null hypothesis is the treated population mean will still equal 3.10. So again, just like step 1 from before, no difference there really at all. We pulled that number right out of the book, and the rest of the formatting is the same. Okay? So, step 2. Step 2, we need to determine our critical regions. Well, we know it's a two-tailed test. The problem told us to use an alpha level of 0.05, but now we have an extra thing we've got to know before we can use the table. We've got to know what is our degrees of freedom. Well, the problem told us that there were 9 people in the sample, so 9 minus 1 gives us 8 degrees of freedom. So now you want to go to your T-distribution tables that we looked at before. You want to go down the degrees of freedom column on the left till you get to the number 8. Across the top, remember the first row is for one tail, the second row is for two tails. So go down to the second row and slide over to 0.05 and slide down to 8 degrees of freedom. And you should find that we have a critical T of plus or minus 2.306. So that's telling us, again, that our T-statistic, which is telling us where our sample differences are located, is either going to be above 2.306 or below negative 2.306. So that step, mostly the same, just a couple little extra things to think about. Next up for us, step 3, doing the math. Well, the problem did not give us sample variance, so we're going to have to get sample variance on our own. Again, that's sums of squares over degrees of freedom, or sums of squares over n minus 1, however you want to think of it. Well, the problem did tell us that the sums of squares was 162. And we already know the degrees of freedom is 8. We figured that out in the last step. 9 minus 1 for 8. So this means that our sample variance equals 20.25. Now I know we can't do this together anymore, but make sure that you're doing this calculation, pause the video or whatever, that you're getting the same answer so that you know you're calculating things correctly. So again, what was the point of calculating this? To replace, to substitute for the missing population variance that we need in our second calculation for estimated sample variance. Or, I'm sorry, estimated standard error. Estimated standard error. So again, that is sample variance divided by sample size and then square root it. So we just calculated our sample variance is 20.25. Our full sample size, not degrees of freedom here, that only happens up there in the calculations. Full sample size here is 9, and then we're going to get the square root of that. So remember, divide first. 20.25 divided by 9 equals, then get your square root function in there, and you should find that this answer equals 1.5. So our estimated standard error is 1.50. And then lastly, all we've got to do is calculate our T-statistic. And again, that's the sample mean minus the population mean divided by estimated standard error. So the sample mean was 6.4. The population mean, we know, was 3.1. And our error was 1.5. So when we calculate all of that, we find that our T-statistic is 2.20. 2.20. Well, back in step 2, we looked at our critical T, and our critical T was 2.306. We've only gotten to 2.2. I'm going to erase this so we can look at it graphically. I miss my big board. .20 doesn't move far enough from 0 to cross that line, so that's up here. So we landed in the body. If we miss the targets and land in the body, what do we do in step 4? What decision do we make? In this case, obviously, we are going to fail to reject the null hypothesis. And if we needed to write that in APA, we would say we have a T of 8. That's our degrees of freedom. So we say a T of 8 equals 2.20, semicolon, P greater than, because we failed to reject, our alpha level of 0.05. So hopefully you see that this is very, very similar to what we've been doing. And that's kind of the theme for the rest of the course. We're just going to keep making little tweaks and little changes to accommodate different research designs. But there's our 4 steps with our example for our 2-tailed single sample T-statistic. So next we're going to flip this, as we usually do, over to a 1-tailed example. The problem even has it already written for 1 tail. So we'll see that in the next video.